Okay, so the official definition here is really important. Diffusion is the net movement of particles from a place of higher concentration to a place of lower concentration. So if we go back to our tea bag, right? Initially, all those tasty tea molecules are super concentrated, jam-packed inside that little bag. Meanwhile, the water around it has a very, very low concentration of tea. Nature sees this imbalance and just gets to work fixing it. So the whole process kicks off with that crowded area of high concentration. Then, because of that constant random movement we were just talking about, the molecules start to just wander out into the less crowded space. And they just keep on doing this until they hit what's called equilibrium. That's the state where they're all pretty much evenly spread out. And just like that, your tea is perfectly mixed. That all seems simple enough, right? Particles just spread out. End of story. But what happens if we change the rules of the game just a little bit? What if we put up some kind of barrier that stops some particles from moving wherever they want? Well, the game completely changes when we introduce something called a semi-permeable membrane. The best way to think of it is like a screen door, you know? It lets the small stuff like air pass right through, but it blocks the bigger things like bugs. In the world of our cells, these membranes are incredibly smart gatekeepers. This special barrier gives us our second key term, osmosis. Now, pay close attention here, because this is where it gets interesting. Osmosis is specifically about the movement of a solvent, and for our purposes, that's usually water, across that membrane. But here's the twist. The water actually moves towards the area with a higher concentration of other particles, the solutes. Now, why would it do that? Well, it's because those other particles, the solutes, are too big to get through the membrane themselves. So the water moves in to try and dilute that concentrated side and bring things back into balance. Okay, so we've got diffusion, the great spread, and osmosis, the selective spread. They're related, for sure, but they are different in one absolutely crucial way. Let's put them side by side to make that difference crystal clear. So the key difference really boils down to two things. First, in diffusion, pretty much any particle can move. Think about perfume molecules spreading through the air in a room. No barrier needed. But in osmosis, it's typically just the water that's moving, and it absolutely has to have that semi-permeable membrane. That membrane is the total game changer. It's what decides who gets to move and where they get to go. Now, this might all seem like some neat chemistry stuff, but it's happening billions and billions of times a second inside your own body right now. So why should you care? Well, because without these two processes, life as we know it would just stop. It couldn't exist. Think about it. Every single breath you take depends on oxygen diffusing from your lungs into your bloodstream. When a plant gets a drink of water, it's using osmosis to pull that water up from the soil. Your kidneys are absolute masters of both, using them to clean all the waste out of your blood. And maybe most important of all, your cells literally maintain their shape by controlling water through osmosis. This is why staying hydrated is so critical. Get too little water and your cells kind of shrivel up. Get too much and they can actually swell and even burst. It's a constant, delicate balancing act. It all really comes down to this one powerful idea. The simple random movement of tiny molecules is the foundation that the entire complex machine of life is built on. It's just an amazing example of how simple rules of physics can create these incredibly profound biological results. Which brings us to a final, pretty wild question to think about. Your cells are constantly managing this flow, right? They're acting as tiny, intelligent gatekeepers. So what would happen if they just lost that control? If you ponder that for a second, it really drives home just how critical this invisible, constant dance of molecules really is for keeping every single one of us alive.